Welcome to this video on the topic of linear functions. In this video, I'm going to show you how to sketch a linear relationship, that being the action of changing the algebraic representation of a linear relationship to that of its graphical representation. Now this is similar to the idea of graphing a linear relationship, however sketching has some slightly different end goals that I'll explain later. Now if we go down, we can go about sketching a linear relationship when we arrange our algebraic representation in something called slope-intercept form. This is characterized by the equation y equals mx plus c. X and y being our coordinates on our Cartesian plane, and m and c representing the gradient or slope and the y-intercept respectively. Now the way in which we sketch a linear relationship in slope-intercept form is the first thing we do is we identify our value of c, so our plus c being our y-intercept. If we have a negative plus c, we mark it on our y-axis like so, or if we have a positive plus c, we simply mark it on our y-axis like this. We then mark it out as 0, c. So what we're able to easily infer from this slope-intercept form is the location of our y-intercept. Now the next thing we need to do is we need to look at the value of m representing our gradient. Now for a positive gradient, what we're going to expect to see is a line that's going to grow like this, and for a negative gradient we're going to see a line that's going to decrease like this. In our case, we're just going to assume that this is going to be a positive because we like seeing positive trends, of which the line itself is going to start at one end of the graph and finish at the other end of the graph. It's going to cut the y-axis at our y-intercept. Now as you're able to see, it's very easy to sketch like this. However, one of the downsides is it's not particularly accurate. The only things that are assured in this particular representation is the location of the y-intercept. The slope and the location of the x-intercept are not going to be accurate. So what you're going to find is that the advantage of sketching a graph over, say, graphing a graph is such that it's all about speed. So you're looking at trends of what's going on with your linear relationship. However, the downside is that you're not going to be able to extrapolate results from the graph itself. You need to get results from the graph, then you need to actually graph it. Otherwise, you can get away with sketching it. Now that we've got this out of the way, let's have a look at a few examples. Example A, sketch the following. We have AI y equals x plus 2. Now the way in which we're going to sketch this is the first thing we're going to do is we're going to locate a value for c, so our y-intercept. This is a value of 2. So as a result, I'm going to go, it's positive, so it's above the x-axis, so I'm just going to mark out 2 like so. From there, we're going to have a look at the gradient, in which case it's a value of 1. So there's nothing in front of the x, so it's an inferred value of 1. As a result, for every 1 we go across, we're going to go up 1. So we're going to get a line that goes on a 45-degree angle. As a result, I can simply draw a line that looks something like this. Notice how I'm not too particularly concerned about the angle of the line. So long as it looks like it's 45, then that's good enough for me. Moving on, I'm going to mark out 0 and 2 on the Cartesian plane like so, and I'm going to put arrows on my line itself. Now to finish everything off, because I can see I'm about to put multiple lines on this Cartesian plane, I'm going to write the relationship of the line, so y equals x plus 2. This makes it nice and easy for anyone looking at your figures to know exactly what line corresponds to what relationship. Too easy. So that's the first one sketched. Notice how fast and easy it was. Didn't have to do a single calculation, but what we're able to infer is the general trend of what this line represents. Now let's go down to AI, so y equals 3x plus 2. What you can see once again is that we're looking at the same y-intercept, so this guy over here. So we don't have to mark that out again. However, what has changed is the gradient. So I've got a gradient of plus 3. This means that the line is going to be steeper than a gradient of 1, so we're going to shoot upwards like that. So as a result, what I'm going to do is I'm going to draw a line with my ruler, best I can, and I'm going to make sure that it runs at an angle greater than 45 degrees. That looks sort of reasonable. I'll mark it with my arrows, and then I'll describe it. Simple stuff. Sketching has never been easier. Alright, final one, we're looking at y equals 0.5x plus 2. Once again, you can see that the constant is unchanged and therefore the y-intercept is unchanged. However, the gradient in this case is significantly different. Rather than being above the value of 1, we've got a value of 0.5. What that means is that the steepness of the line is significantly less. So if we had 45 degrees for a gradient of 1, then we're going to look at something like 22.5 for this 0.5. So I'll get a line that's roughly half the steepness of before, and I'll retrofit it. Next thing I'll do is I will label it. Done. So what we've been able to easily achieve here is representing these algebraic expressions seen here in their graphical form seen over here. Now, as I mentioned earlier, one of the downsides is that you're only really able to show the trend of the graph, and the only guaranteed point on this graph that will be accurate is the y-intercept. Now, if you want to represent more information on the graph, which you probably should do if you're asked for it in a test, what you can do is you can bring up your calculator and you're going to go across into graph mode, so 5. From there, you're going to type in the linear relationships in their slope-intercept form. So y equals x plus 2, 3x plus 2, and 0.5x plus 2. Once we've got those in, we can hit F6 and it will graph them for us. Now, if your graph doesn't look like this, what you can do is you can go to zoom and then you just hit auto and it will try and figure it out for you. Basically, what you're trying to do is you're trying to show the feature on the graph that you're trying to get the value of. In our case, we want to get the intercepts here. We'll say for this one and this one. We won't worry about this one because it's not shown here. So, to get the intercepts themselves, what we're going to do is we're going to press F5 for Gsolve. Then we're going to hit root. Root simply means the location at which we cut the x-axis. Now, the first one being highlighted here is our middle one. So I'll hit execute and it's going to tell me that it lies at a value of -2 and 0. So I can simply retrofit that coordinate onto the graph. Too easy. Next one is, we'll go for this red one here. Gsolve, root, and we'll navigate over. So not this one again, but this one. It's going to be an intercept of -0.6 and we'll round it to 7. And thus we've done the sketching of these 3 linear relationships here. So remember, when you're sketching, it's not necessarily going to be accurate. You're simply denoting the general trend of what this linear relationship is doing. If you need accuracy, as in you're going to be pulling points from this graph, or you're trying to solve simultaneously using graphing, then you need to actually graph the relationship. You cannot sketch it, you must graph it. Alright, going down we have B. We have y equals -2x minus 1. Sketching this, we first observe the y-intercept, which is at -1. So, on my y-axis, I'm going to locate -1, in which case my axis isn't labeled, so I'll just put a cross through here and say, this is now 0, -1. Now looking at the gradient, we have a gradient of -2. So what this means is we're going downwards. We're going downwards and we start at 45 and then we're like, nope, we need to be steeper. So we go down at a faster rate. Make sure that the line cuts where I've said it should cut. And then I'll make it nice and pretty with some arrows. Boom, we've managed to sketch the linear relationship y equals -2x minus 1. Alright, next one across we have BII. What you can see is that this linear relationship here is not in slope-intercept form, rather it's in general form. Now if we wanted to, we could graph this. However, the issue with graphing this on this particular Cartesian plane over here is, well, it's not really set up accurately, so you wouldn't want to mix the two. Rather, what I'm going to do is I'm going to rearrange this into slope-intercept form and then I'm going to sketch it. So to do that, I am going to go take 2x from both sides, then divide by the coefficient in front of y. this will yield y equals minus x minus 1. Okay, this is now the linear relationship that we want to sketch. Looking at it, what we find is that our intercept itself is at -1 again, so it's going to cut through this point, and we have a gradient of -1. So what this means is that we're going to get a line that goes downwards at roughly 45 degrees. It's a pretty horrible line, so I'll draw a new one. Make sure I'm using my ruler. Alright, that looks reasonably okay. Now you've got an option of how you want to represent this line here. You can either annotate it with this form over here, or you can annotate it with this form over here. Because I like the idea of showing that this form itself still is the same as this equation over here, I'm going to write the general form of it on the line. Too easy. Now if we wanted to get features such as the x-intercept, we can simply bring up our calculators, we'll hit exit, we'll turn these functions off by pressing select, and then I'll key in the two other functions that we're using. So it was minus x minus 1, that was this function here, and then it's going to be minus 2x minus 1. Notice that I'm putting in the slope-intercept form of this relationship here, that being that the calculator doesn't accept general form. Alright, pressing F6, I'm going to graph both of these relationships, and then I can zoom in if I want. So I move the cursor over the function and just zoom in to get some more detail. There are ways in which you can automatically set up the window, so you go through these settings, but for now I'll just keep it simple and use the zoom functions. Basically, you won't use V-window unless you explicitly know where you're supposed to be looking, or whether you've got a very proficient understanding of how the curves are going to behave. Now, finding the intercept of this guy over here, the one in general form, we'll go to gsolve root execute, and that will be at -1 and 0. Now for the second one, so this guy over here, we're going to go to gsolve root, then we'll highlight the next one. That's at -0.5 and 0. So I'm very easily able to retrofit the information on the graph. Now one thing you're going to see is the inaccuracy of the sketching here. So down here, for every 2 we go down, we're at -1, whereas what's seen over here at -0.5 you'd expect to be somewhere around here. But remember, because we're sketching and because we've annotated the exact point, it's okay. You just need to remember you cannot pull points from the graph itself. Alright, now next one is C, y equals -1/2 x minus 3. Plotting this, what we're going to do is we're going to say, well, -3 we'll say is here, and we'll go 0, -3. Observing the gradient, we have -1/2, so that's going to go downwards, and it's going to go at a more shallow downwards, like so. Annotating, you have y equals, easily done. Alright, next one we have y equals 0.5, or next one we have y equals 0x plus 1. What you're going to find is that the coefficient in front of x here is 0, which basically means that we're dealing with y equals 1. Now to be able to sketch this, what we're going to need to do is we locate our constant c, which is 0, or sorry, constant c, which is 1, and we mark it out on our graph. In this case it's here. Now because we have a slope of 0, what that means is we're going to flat line like so. So using a ruler, all I need to do is draw a straight line. So this is y equals 1. So y takes on every value of 1, no matter what value x is. Alright, final one, x equals 4. Well, if y was a horizontal line, then the next one is going to be a vertical line. So we're going to locate the value of 4, which is over here. And I'll mark it out as 4, 0. And then I will carefully shuffle this guy across here so it doesn't get in the way. Then I'm going to draw a vertical line. So for all values of y, x is going to equal 4. And what I should have done is I should have marked this out. And thus, what we've been able to demonstrate in this particular video is how we can go about sketching linear relationships. Now remember, the sketch itself isn't necessarily going to be accurate. Rather, it's going to be a representation of the general trend of the linear relationship. Now you can sketch more than just linear relationships. You can sketch exponentials, you can sketch quadratics, you can sketch all sorts of polynomials. However, all we're doing when we sketch something is we're simply trying to show the general trend of what's going on. So if you need more accuracy or you need to pull information from the graph itself, then you need to graph it.